Okay. Hi, we're here today with CJ Morel. This is Lucintel, and we're going to be learning about some pretty exciting new technology coming to light, which is called biological intelligence. And your company is
Vivum AI.
Vivum AI. Can you kind of, in a short, simple as possible way, kind of tell us what is biological intelligence?
Biological intelligence, so it's artificial intelligence based on biology. So in today's traditional classical AI, it's linear math, NVIDIA GPU chips,
You said algebra.
algebra. On dynamic neural models based on biology, the better math is ordinary differential equations with time constants. They can better represent the neurons and synapses of our brains because that's the most efficient computer on earth is our human brain.
And so what makes this better and different than generative AI, what we're seeing right now as the buzz?
That's a great question. And so I don't want to say it's better. I think it is.
Yeah.
Generative AI does some wonderful things. But in the end, today's AI has to be trained on a fixed data set.
Yeah.
Okay, and so I train it for days and weeks, and at some point I release it into the public domain, and it'll work fine as long as you ask it to do things it was trained on. But as soon as I present a scenario that it hasn't been trained on, all bets are off in terms of what answer am I going to get at that point in time. It will try to get the best answer it can, but it's somewhat guessing at that point. And the information that it uses to make that guess will be fed back into its algorithm to make the next best guess. And eventually that model starts to drift. And that's why we have things like ChatGPT 4.0. Eventually we'll have ChatGPT 5.0, 6.0, because it has to be then retrained and then re-released. Dynamic neural models based on biological intelligence aren't trained. They're evolved, like you and I, over the course of generations. And they, instead of having a classical AI where I give it an input and I get an output, with dynamical neural models, they create emergent behaviors. They evolve in a behavior that says, I have many choices to go from point A to point B based on the context and intent of what I was trained to do. I'll pick the best path that I think I should take at this point in time, as opposed to saying there's only one path from A to B. No, there could be many choices, and based on what my task was programmed to be, I'll pick the best choice of many choices for that particular task.
So it can think outside of its data that it's been given.
Like you and I do when we're presented with a scenario where we've never seen this scenario before, but our intelligence and our evolution says, based on what I know and my knowledge, and how I was brought up and where I was brought up, I think this, and this are the best way to approach it, and I'll go approach it that way. And if it's a good approach, I'll remember that. If it wasn't the best approach, it took me twice as long to kind of get there, I'll learn from that and not make that mistake again the next time around.
I like the way you had told me earlier with the, if someone touches a hot pan, they'll know, oh, that's hot, don't do it again.
Don't do it again.
And
with that, it'll say, I don't need to know exactly the same stove and color and type for the next time. I know enough now that something that looks like that could be dangerous for me.
And that's something right now generative AI cannot do at all.
It doesn't understand context and intent, so it wouldn't make that. If you trained it for that, it would. But if it never saw that scenario, it wouldn't really know what to do.
Yeah, and can you tell me the best use case scenarios for this AI to be used? Like for writing and stuff, generative AI is great.
That's right, exactly. So if today's classical AI likes to have discrete data sets that it could be trained on.
Yeah.
And that's great. But life kind of moves forward all the time. Like time is part of life. And so these models are built with time constants. Time has evolved. So in any environment where the data is going to dynamically change, that's where these models will thrive as opposed to a static database of data that I have to work with. I want to be these models. I'm going to pretend I'm a dynamic neural model. I want to live in an environment on the edge because I'm very efficient. I'm going to take very little power. I'm really smart, but I want to be fed all kinds of data immediately all the time, and I'm going to evolve and learn from that.
Okay, and you said the main difference in the way that this was created versus generative AI was through evolutionary algorithms and differential equations.
That's correct, with time constants.
Can you explain the time constants? I think I'm still a bit unclear.
So an ordinary differential equation with time constant means that if I create an algorithm, a model with, let's say, 6 neurons, these neurons are all connected to one another, and each neuron is represented by an ordinary differential equation with time, meaning that the data is going to come at me dynamically. I'm always moving forward, whether a microsecond, a half a second. Time is involved.
Yeah.
If I take, as an example, if I take ChatGPT and I type a question in the ChatGPT, I hit a return, I get an answer back on my screen, but there's no time involved there. I could have waited forever before I hit the return key to get an answer. When I hit the return key, I got an answer in a couple seconds, but there's no time constant involved. With dynamic neural models, to survive, they want to be moving like a shark. They want to move forward. Yeah. They want to be fed dynamic data all the time. And because of that time constant, and because they're all integrated together, their compute capacity is exponentially greater than we call that a dynamical neuron, is exponentially more compute capable than a standard vanilla neuron in classical AI. Now, to go beyond the technology at that point, we need to be a PhD to have that discussion.
Is what you mentioned, right?
Dual PhDs, correct.
And that kind of answers a bit. One of my other questions I was going to ask is, this is such an awesome concept, right? Why aren't we seeing more of it?
That's great question. Great question. There are 3 groups in the world right now that are working in this area. There's a Chinese university, there are our team, and then a bunch of guys that left MIT to do the same thing. These models were developed replicating neurons and synapses over the last 50 years by dual PhD scientists.
Yeah.
But you needed to be a dual PhD, and you needed a supercomputer to run the algorithm. What our team was able to do is figure out how to create software tools that will allow other mere mortal engineers to create their own algorithms, dynamic algorithms, and it'll run on an FPGA. So they don't need a supercomputer, I don't need a GPU. A standard vanilla off-the-shelf FPGA is all that's required. And if you don't have the FPGA, it'll run on a microcontroller or a CPU. But
I think that's also such a cool detail that I can work on all these various platforms.
You could implement these algorithms on existing compute platforms today. You don't have to spend any more money on hardware.
Amazing. And my final question is, I know we had talked about kind of defense applications of this product. Could you tell me that example you were telling about the drones, how this is so different because of the issue that can be faced by a drone with the GPS signal, and how this form of AI would react? That's right.
So a lot of challenges with drones in any situation is a drone uses the GPS signals from satellites to orient itself and know where to go.
Yeah.
In some examples, like in battlefield examples, if your enemy is jamming the GPS signal, I've now lost all sense of direction. And in that case, drones typically fall out of the sky at that point. They don't know where they're going. Like you and I, if we're given a map and we get in a car and we're told to drive from Las Vegas to LA, we're gonna do fine with the map, right? It's not Google Maps on the phone, but it's just a paper map. Yeah. But if that paper map blows out the window, I'm on my own at this point. So what do? We
put a stick in the sand.
We put a stick in the sand. We look where the sun is. We configure time. We configure direction, east, west, north, south. I say, hey, the mountains are over there. LA's in that general area. I'm going to keep going because I know I got enough gas. As humans, we work through all those.
Outside of the box a bit.
That's what thinking outside of the box, and that's what these evolving models do. If you're flying through a battlefield and you lose GPS, the model says, okay, what do I have left? Well, if there's a camera on the drone, I'll switch to vision now. I'll say, okay, I have eyeballs. I don't have sense of direction, but I have eyeballs. Do I know enough? I know where the sun is. I can see these geographic points. Do I have enough information to complete the task that I was programmed to do, which is to get to LA? If I don't, should I stop and wait for a while and see if GPS comes back? Or I actually know where I came from, so I'm going to turn around and go back.
Yeah.
All that decision is made on the algorithm on the drone. So quite frankly, the drone is autonomous at this point. These models deliver legitimate autonomy to an embodied system. Think of a drone, a robot, an autonomous vehicle, a network here at the telecommunications conference, embodied networks where the data is moving quickly, and you want to be on the edge and you want to consume very little power. This is the perfect solution, the AI solution for you.
Yeah. Awesome. Thank you so much. This is incredible technology. I'm excited to see where it goes.
Thank you very much. Very nice meeting.
Thank you so much for watching. Check out the link below to read the full article on this topic and to see others like it, and to also gain access to our website where you can see our further capabilities in consulting and market research.